Okay, so this lecture actually I've set chapter 10 here, but it actually the transition from chapter 9 to chapter 10, and it's kind of actual chapter 10 will start from the next lecture. But anyway, I'm not sure this could go in chapter 9 or it could go in chapter 10. Uh, well, anyway, it doesn't matter where it goes. Okay, so this is the circuit we'll start with, and actually it's an RL circuit, so it is not even an RLC circuit. So in some sense, this could even have been chapter 8, and it doesn't matter. The question we are asking is, we have this simple RL circuit, we have a voltage source, and the switch is closed at t equal to 0. It was open for t less than 0. And Vs is given by Vm cos omega t. So Vs is a sinusoidal voltage source. All right. So this is the new thing we are starting from this lecture onwards, and we will continue for the next few lectures. Method is the same. So we go through the three steps. So for step 1, t less than 0. So I'm not drawing the circuit each time because this is very simple. So the switch was open, so the current was 0. So we say I equal to 0. At t equal to 0 plus, the inductor current does not change. So it will still remain 0. And we directly go to step 3, which is the circuit for t greater than 0. And if we write a KVL around this loop, we stay very straightforward. R times I is the voltage plus L di dt is this voltage equal to the voltage source. So we'll get L di dt plus Ri equal to Vs as the differential equation for this circuit. And we've derived this before anyway. Only now Vs is a sinusoidal form of voltage source. Now again, the other thing we note is that this is a non-homogeneous equation because the right hand side is not 0. Now actually there are two ways of solving this equation. Because this is a first order equation, one could directly do separation of variables and solve for I, but I am doing the method of natural response plus force response because intuitively, as you will see in a minute, this is more easy to visualize. Okay, so we say because this is a non-homogeneous differential equation, the solution of the differential equation can be written as the solution of the homogeneous part of the equation plus any solution of the non-homogeneous differential equation. Now the homogeneous part we've solved before. This is if this was the right hand side is 0, that means if the voltage source is shorted, then we have just an RL circuit, and the solution of that is simply a first order exponential. So we know that the form of the natural response is a e raised to minus t by tau, where tau is L by R and a is some constant. What is IF? Let us think about IF now. Now, as I have mentioned in the last lecture, because Vs is a sinusoid and because this circuit is linear, IF or IF specifically will also be a sinusoidal function with the same frequency as Vst. Alright, that's a property of linear functions. So I'm asking you as homework, can you demonstrate this statement just for the resistor, in an inductor, a capacitor and a diode? This statement that if so in this case, if the element is linear, and let us say I apply a sinusoidal voltage source to any of these elements R, L, C and diode here, then show that the current will be sinusoid if the element is linear. Alright, voltage source is applied, sinusoidal. This box can be R, L, C or diode, and the diode equation is this. Then the current will be a sinusoid of the same frequency as Vs if the element is linear. It's a straightforward thing, but it's an interesting thing to do. Alright. So we say, and of course this we see that this is true. So we say IF will be a sinusoid, but of course it will have its own magnitude and a phase. So we say, well, let IF be some magnitude Im cos omega t, where omega is the frequency of the voltage source, minus some phi. I'm putting a minus for a reason. We'll come back to it in a minute. It could be plus, it doesn't matter. So this is a general form of IF, and we can expand this cos omega t minus phi as Im cos omega t cos phi plus Im sin phi sin omega t, and I'm defining Im cos phi as some b1 and Im sin phi as some b2. So cos omega t sin omega t. Then we say if this is IF, then IF must satisfy our differential equation, which is L dIF dt plus RIF equal to Vs. So we substitute for IF from here, and then we differentiate IF and substitute that in the differential equation. So IF is this. So dIF dt is, so this is L times dIF dt. So we have to differentiate this. Differentiate this. I'm taking this form again for a reason. So the derivative of IF or derivative of this is minus omega b1 sin omega t plus omega b2 cos omega t. So minus omega b1 etc. That is the first term plus r into IF. So IF is b1 cos omega t plus b2 sin omega t equal to the right hand side, which is Vm cos omega t. Vs is Vm cos omega t. Now we combine the sine terms on the left hand side and the cos terms on the left hand side. So we write this as minus omega L b1 plus r b2 sin omega t plus omega L b2 plus r b1 cos omega t equal to Vm cos omega t. Alright. Then I take this cos omega t term on the right hand side. So we'll get minus omega L b1 r b2 sin omega t equal to Vm minus omega L b2 minus r b1 cos omega t. Alright. Now we say for this equation to be true for all values of time t, the coefficients of the sin omega t and cos omega t must be 0. Why? You tell me. I am not answering that question. I think you know the answer. I will ask this in our discussion session on Thursday. So let me go back here. The statement I am making is, for this equation to be true for all values of t, this coefficient must be 0 and this coefficient must be 0. Alright. So you answer why that has to be from a mathematical perspective. Okay, so we take that as for granted, and we'll say omega L b1 plus r b2 equal to 0, which gives us b2 in terms of b1, and then this term equal to 0, and so we substitute for b2 and we get b1 equal to r by omega square L squared plus r squared into Vm, and b2 equal to omega L by omega squared L squared plus r squared Vm. Substitute this back in I of t. Alright, so this was our natural response plus this is our forced response. So this is the total solution of I of t. Yeah. Now we can impose an initial condition. What was the initial condition? That I of t was 0 at t equal to 0. And you will be able to find A. It's straightforward. I'm not doing it. Please do it so that the solution is complete. So you can see from here that at t equal to 0, this will be 1. Cos omega t will be 1. Sin omega t will be 0. So and it is 0. So we'll get A equal to minus of this coefficient, alright, minus of Vmr by omega square L squared plus r squared. Alright, some value of A will come. For now, you do this on paper. Now here is let me see 1 second. Okay, now this is a very, very important equation. What this is telling is that when we close the switch of that circuit, let's go back to that circuit. when we close this switch at t equal to 0, the current, and so the currents and voltages in this circuit will have will be a sum of two types of functions. One will be an exponential function, the other will be sinusoidal. The exponential is the natural response that any RL circuit or any circuit with RLC has, and this is caused by the fact that we've applied a sinusoidal voltage source to the circuit. Now this, the so-called the natural response or the transient response will die out as a function of time. It has an exponential. So over a period of time, when t is like greater than 10 times tau, etc., this will effectively become 0, and all that will be left is the second term, which is the sinusoidal term. Therefore, this term is referred to as the sinusoidal steady state response. Sinusoidal, of course, obviously, steady state because this is the response of the circuit once the transient has died out, and the transient will die out as a function of time. So once the transient dies out, we say that the circuit has reached sinusoidal steady state. Alright, so this is a very important thing to recognize. We'll talk about this more just in a minute. Okay, I am also writing this in a different form. So where is the solution? So this is the solution of the sinusoidal steady state solution. So there is RVM and the denominator cos omega t, omega L Vm and the denominator. Alright, so I'm saying this is R and this is omega L. So I'm saying let R be equal to x cos phi, let omega L be equal to x sin phi. Now you can convince yourselves that it is always possible to write any two arbitrary variables in this form. You tell me why this is possible. It is actually, you know this from 12th standard, but just kind of remind yourselves of the 12th standard physics or mathematics and tell me why it is always possible to write any two constants in this form. So if we write this, then of course we say this squared plus this squared, will the cos squared plus sin squared will become 1, will be r squared plus omega squared L squared, and therefore x is equal to this, and then this divided by this will give us tan phi equal to omega L by r, and so phi is equal to tan inverse omega L by r. And so we can write the IFT, the forced response, as Vm by this, the prefactor, into, so this is x cos phi is r and x sin phi is omega L. So we can write it in this form. And then this of course is cos omega t minus phi, and the x comes out. X is this, so the denominator becomes a square root. So we can write IF in this form, which is a magnitude times cos omega t minus a phase. Now this is minus implies that IF lags Vs. So Vs was cos omega t, IF is omega t minus phi, and phi is a positive number because this tan inverse omega L by r is positive, and therefore the current, one says, kind of lags. It is delayed. The voltage reaches first and the current follows, and that is what this negative sign indicates. And this is a property of inductors, that the inductor current will lag the inductor voltage because the current in an inductor takes time to change. The voltage can change instantaneously. If you solve the same circuit with L replaced by C, you will find that this turns out to be positive, because in a capacitor the current leads the voltage because the voltage cannot change instantaneously. Alright, so we found IF of t. Let us do more analysis. Okay, so as I said here, what we found, just to repeat, is that when we open or close a switch, there will be a transient, and the transient will die out. And if the input is sinusoidal, then only the sinusoidal part of the currents and voltages will remain. Now, there is a very large number of circuits and systems where one is interested only in the sinusoidal steady state response. One is really not interested in this transient response. So I'm sure you can think of what these systems are. These systems are all our electrical, everything electrical, right? Fans, lights, everything that is connected to our power supply, the 220-volt power supply. So when you turn on a switch, the fan turns on, or the light turns on, or the AC turns on. And we are really not interested in what happens for the first few milliseconds during this transient. We are really interested in what happens to the system once the transient dies out. We are interested in the sinusoidal steady state response of these systems. There are, of course, some people, the specialists who design these AC distribution systems, who are interested in the transient, but the user is not interested. And they're given this. Special methods have been developed given the fact that all our power system is sinusoidal. I didn't mention that, but I assume that you know that all our the power that comes through in our plugs and in our house is sinusoidal, and so the sinusoidal systems are ubiquitous, they are everywhere, and therefore special methods have been developed to analyze circuits in sinusoidal steady state. All right, so now with this we are transitioning to chapter 10. So chapter 10 is about analyzing circuits in sinusoidal steady state, which means we have all input voltages and currents sources are sinusoidal, and we want to analyze circuits only for the steady state. We don't care about the transient response of these circuits. All right, so we assume that everything is sinusoidal and see how to solve. So let us look at how or what is done to solve these circuits and what simplifications are used. I'm not sure simplification, but techniques is a correct word. Okay, so let us think about this thing called a complex forcing function for a few minutes. So we note that, as you are familiar with this Euler identity, cos omega t plus j sin omega t is e raised to j omega t. J, by the way, is square root of minus 1, as I had said before. This is I in mathematics, j in electrical engineering. And we note that the derivative of an exponential is an exponential. We say, well, let us try applying a complex forcing function to our circuit. This circuit we just studied in detail. We just finished the last part of this, the first part of this lecture. So we say now instead of Vs being Vm cos omega t, let Vs be Vm e raised to j omega t. And we do this because of this property which we want to see if we can exploit. The fact that the derivative of an exponential is an exponential and this complex forcing function is exponential. And I put a bar over this because now this is a complex function, so it will have a real part and an imaginary part. And again, because of this property, we say let if be also an exponential. All right. If the forcing function is exponential, and then for a linear circuit, all the currents and voltages will also be exponential. So we say let if, which is what we want to find, also be exponential. Then we substitute IL in our if in the differential equation, which was L di by dt plus Ri equal to Vs. So L into the di dt of this, which is B into j omega into e raised to j omega t plus R into B e raised to j omega t equal to Vm e raised to j omega t. Now e raised to j omega t cancels. As we have seen, of course, before when we were solving second order equations and we had substituted e raised to st. This is the same algebra but with a different result. So now we cancel e raised to j omega t and we get b something something equal to Vm e raised to j omega t. Now we can find b. Oh, I'm sorry. This e raised to j omega t is not there, of course. It is not there. So we'll get b j omega l plus r equal to Vm. Alright? And so b is equal to Vm by j omega l plus r. And so we substitute b here and we get an expression for if, which is if equal to Vm by r plus j omega l e raised to j omega t. Now we saw already, you remember that r plus j omega l. So let me go back. Here, r plus j omega l can be written as r squared plus omega square l square square root into this. So we utilize that. R plus j omega l has a magnitude and a phase. The magnitude is this, the phase is phi, and so we can write r plus j omega l as this. Alright? Okay, am I making sense? So r plus j omega l is x cos phi plus jx sin phi, and x is this and phi is this. Alright, okay, so now it makes sense. So r plus j omega l is x cos phi plus jx sin phi. X we take out, x is this, and cos phi plus j sin phi. This, using Euler's identity, can be written as e raised to j phi, right, where phi is equal to tan inverse omega l by r. So this we substitute here for r plus j omega l, and therefore we write if of t as Vm by r square plus square root into e raised to j omega t minus phi. Alright, I hope you can see this. So Vm e raised to j omega t divided by this. So this is here, and the e raised to j phi goes up, and we will get e raised to minus j phi. And I am writing Vs again. And now let us compare. So we derived first, if the forcing function was Vm cos omega t, we found the inductor current, the sign steady state current to be all this. If the forcing function is this, the complex version, then the current turns out to be Vm by all this e raised to j omega t minus phi. Alright? Real, complex. Real, complex. This is of course only mathematical. In real life there are no complex, but we are just doing this on paper. So what we realize is that the actual Vs that we have applied can be written as the real part of the complex forcing function. If that is the case, then the current that flows in the real circuit for the real forcing function is a real part of the complex current that we obtained by applying a complex forcing function. Now this, again, this is a property of linear systems, and it's an extremely valuable and important recognition or result. Okay, let's do one more quick analysis, then we'll formulate the method. Alright, so let us say this is our circuit. So current source in parallel with RLC, and let Is be a sinusoidal Im cos omega t. Then we saw that for ILT, we have derived before, so I am not deriving it again. So it is LC d2 IL dt squared plus L by R dIL dt plus IL equal to Is of t, where Is is this. Then we say, now let us make Is a complex forcing function. Alright, so we say Is is converted to a complex function. So instead of Im cos omega t, we say Im e raised to j omega t. And then we say, well, let us assume that for this forcing function, IL, the current in the inductor, has the form A e raised to j omega t, because if this is exponential, this will be also exponential. If IL is this, then dIL dt can be found. There's a derivative A j omega, and the second derivative will be A minus omega squared e raised to j omega t. Alright, and then we substitute this back here, all this. So this is a big expression. So actually let us go through this. So d2il dt squared is A minus omega squared e raised to j omega t. So this is minus omega squared A, which comes here. So we'll get minus omega squared ALC L by R into A j omega, which comes here, L by R into A j omega, and IL will be simply A, and the e raised to j omega t, of course, will cancel. Alright, so once the e raised to j omega t cancels, we can find A in terms of all known quantities, Im minus omega squared LC plus 1 plus all that. And if this is A, then IL of t, IL bar of t is this A into e raised to j omega t. And then we say, well, IL, the actual IL, is a real part of the complex IL. Alright, so what happened here? What happened is that because we use the complex forcing function, we did not have to solve the differential equation for Is at all. Alright, we converted the differential equation to an algebraic equation and we solved the algebraic equation. And therefore this is our conclusion. So for sinusoidal steady state analysis, if we assume complex forcing functions, then if the circuit is linear, all currents and voltages will be of the form some constant times e raised to j omega t. Alright, where I and V will be complex numbers. Alright. Now, if that is the case, then for complex forcing functions, let us, if the function is complex, then we can say that the inductor current and inductor voltage will be of this form. Some complex constant times e raised to j omega t for both current and voltage. But we also know that V is equal to L dIL dt. So we can say this is equal to L times d dt of this. And therefore we differentiate e raised to j omega t. And so we get j omega Li e raised to j omega t. And then the e raised to j omega t cancels. So we get a relationship between this I and this V for an inductor. And that relationship is V bar equal to j omega L I bar, where now we call this j omega L as the impedance of L. I assume you've seen this before in your 11th, 12th. I think many of you have seen. I am not sure if you have gone through this process of deriving it the way we just did. Alright, so the derivation is good for those of you who are curious to know where it comes from. It is not critical because based on all this, we'll write a method, and that method is what we will use subsequently. But it is important to understand the theory so that one doesn't mess up. Alright, similarly for the capacitor, we say the capacitor current is of this form, I e raised to j omega t. The capacitor voltage is of this form, V e raised to j omega t. Then we differentiate, and so we get j omega c V, and the e raised to j omega t cancels. And this becomes the relationship between the current and the voltage for the capacitor. So V is equal to 1 by j omega c into I, where 1 by j omega c is the impedance. By the way, you can convince yourselves that omega L and 1 by omega c have the dimensions of ohms. Alright, you must convince yourself. Okay, with all this, now we state the process. So we say if all voltage and current sources in a circuit are sinusoidal with the same frequency omega. So we have a circuit where all independent voltage and current sources are sinusoidal of the same frequency omega. If that is the case, then we can replace or convert, whichever word you want to use, these sources to complex exponentials. If we do, then all the differential equations will become algebraic equations, and these algebraic equations can be solved using all the circuit techniques we have studied. And once we solve them, we will get currents and voltages in the circuit which are complex, and the final answers, the currents and voltages, the actual currents and voltages in the circuits will be the real parts of the complex expressions. Alright, so this defines, in very brief, we'll illustrate this, but this defines how we solve circuits in sinusoidal steady state. And in order to do this, what we'll do is we'll replace inductors and capacitors with their impedances 1 over j omega c and j omega L. So let us illustrate this. Start by illustrating with the simplest circuit here, RC. We did RL, so let us do RC now. So we say let Vs be Vm cos omega t, and we want to find the capacitor current, well, the current in this circuit. So the first thing we do is we convert the circuit to the complex domain and remove the e raised to j omega t terms. So we say Vs is equal to Vm e raised to j omega t plus phi. Then we remove the j omega t as we've seen before. So Vs becomes Vm e raised to j phi. The resistor stays as R. The capacitor becomes 1 over j omega c. So then we redraw the circuit. The circuit is the same, the component values are different. So Vs becomes Vm e raised to j phi. The capacitor becomes 1 over j omega L. Now this is called the complex domain circuit. It is also called the frequency domain circuit, because what we've done is we cancelled e raised to j omega t, right? So let's go back here. Let me find it. So we cancelled e raised to j omega t, alright, as an intermediate step. And once we cancel, the circuit does not have time. This circuit, when it is drawn, there is no time in this circuit. This circuit is everything is in terms of time. Here, actually everything is in terms of frequency, omega. So this is also often called a frequency domain circuit. Alright, so in the frequency domain circuit or the complex domain circuit, there is no t. Remember this, a t should never appear in this circuit, because the e raised to j omega t was cancelled. And now everything is algebraic. All the current voltage relationships for inductors, capacitors, of course resistors, are all algebraic. There is no derivative left. And now we can apply all our methods of circuit analysis to this circuit, as we'll see with many examples in subsequent lectures also. Then we solve this circuit. So we solve this circuit. So now we want to find this current. We have a voltage source. We have two impedances. So we say the current is simply the voltage divided by. So these impedances add, just as resistance is added in DC circuits. These impedances add as they are in series. So we say R plus 1 by j omega. Oops, I'm sorry. This is j omega c. I'm messing up here. But this is c. Alright, 1 over j omega c. Alright. So yeah, so the current is the voltage source divided by the sum of the impedances, R plus 1 over j omega c. Then we bring the j omega c up and we get this form, alright. So we found the current already. Just in 2 steps, we found the current, of course in the complex domain. Now once we found an expression for the current in the complex domain, we must write it in the form, this form, a magnitude, a real magnitude e raised to j theta. So magnitude and phase, where IC is a real number. Okay, IC is no longer a complex number. So we must convert this to a form where the prefactor is a real number and then there is a e raised to j theta c. Alright, so how do we do this for this? Let us do it. So this is the form. Where is it? IS. So this is Vm j omega c by 1 plus j omega rc e raised to j phi. And this alright, so the best, okay, so there are many ways of converting this to magnitude and phase, this specifically this fraction. So we'll encounter a lot of fractions. So there are many ways of converting a fraction to a real, I mean a magnitude and a phase. The most efficient method is to convert the numerator to a magnitude and phase and the denominator to a magnitude and phase. Alright, so j omega c, the numerator of course has no real part, so the magnitude is simply omega c and the phase is 90 degrees because j is the same as e raised to j 90 degrees. The denominator can be, we've done this just a few minutes ago. The magnitude is this and the phase is theta equal to tan inverse omega rc. Well, okay, so this conversion, I'm sure you've seen this before and you recognize, is basically a conversion from rectangular coordinates to polar coordinates. That's all we are doing here. Only we are writing it in a complex form. And you will, okay, so the conversion from rectangular to polar and polar to rectangular will occur all the time now in this chapter in sinusoidal steady state analysis, and you need to become proficient at doing these conversions from rectangular to polar and polar to rectangular. And all your scientific calculators, if you look at them and you figure out, each one of them has a way of converting directly from rectangular to polar and polar to rectangular. Alright, so you'll have to learn for your own calculator. So you just put in so for example here, the real and so 1 and omega rc or whatever, actually of course for calculator you need numbers. So whatever 1 and 5, let us say. So you say, let's say 1 plus j5. So the calculator will allow you to put in 1 and 5 and it will tell you what is the magnitude and what is the angle or the phase of that rectangular coordinates. Alright, so you need to figure out on your calculator, specifically on your calculator, how to convert rectangular to polar, polar to rectangular. Every time you should not be doing square root 1 x squared plus y squared and tan inverse y by x, if this is x plus jy. Every time you do that, that takes a lot of time. The calculator will do it directly for you. Okay, so here this is the form. So it's omega c e raised to j 90 degrees divided by magnitude phase, and then you combine all the magnitude, so you get omega c Vm, the denominator, and combine the phases, so e raised to j phi plus 90 degrees minus theta. So this is written in the form magnitude, real magnitude e raised to j phase. Note that theta is always less than 90 degrees. Theta is tan inverse omega rc. This will always be less than 90 degrees. You should convince yourself of this. And therefore 90 minus theta is greater than 0. So this quantity is positive and therefore IC leads Vs. Alright, because this is a capacitor, the current will lead the voltage. Okay, and so once we have this form, then we convert this complex back to time domain. So we have magnitude and phase, and therefore we write the time domain current as the real part of the magnitude times e raised to j omega t plus the phase. All right. So we say so ICM is the magnitude, theta c is the phase, and so the final expression for ICT is the magnitude ICM cos omega t plus theta c. All right. So also all of this is here. All right. So we'll do many more examples next time. This is the end of this lecture.